Greetings and welcome to the presentation of our final computer-aided engineering project. So we worked on an isothermal mug as our study. This work is done by me, Qasim Shawqi, but as well as Anas Marqa, Ahmed Amin, Saad bin Bilal, Ahmed Younsi, and Sibati Bashir. So without further ado, this is the outline of our project. So you see there are a lot of bullet points, and meaning a lot of work. And since we put a lot of effort into this, we resumed everything into a Gantt chart. Okay, so this is a classic outline, and this is the Gantt chart that we decided to make for our project. So each one of us had a task, either design or MATLAB or the report, and finally the presentation. So to introduce our project, we know recently, or we witnessed recently a high demand in thermal flasks or isothermal mugs. It's something that is more common in a lot of countries. So engineers, of course, based on this demand, they do what they do best, meaning design best isothermal mug. And for this reason, our project is interested in designing and optimizing the best thermal flask for AUI students, which explains the logo here. So this is basically the final model, as you see in the picture. It looks something like that. And it attempts to align features of agronomic, ecological, and of course sustainable and affordable aspects. So now the objective and expected results of our project. First of all, most important thing is the thermal retention performance. So our flask or our mug has to be efficient in terms of retaining heat, either cold temperature for a long time or hot temperatures over a long time. So just retaining the initial heat for a long time. Also material effectiveness. So this thermal retention has to go through a thorough material selection, and that is also ecological, of course. Then the design optimization. So our work should be optimal. It shouldn't be just a lot of materials thrown out there, and this is why our model, we made sure that it is agronomically studied in a way that meets the user's need, and of course following the international standards, because here we're dealing with beverages and container, so of course our design has to follow these, and so that we have a satisfied user. So now for the SWOT analysis, of course we used to do this in Introduction to Engineering Design, so I'll go through it very fast. So for the strengths, as we said, good thermal retention, that's number one, of course. High quality materials, which is also less costly, because we need something affordable. The design should be optimized, of course, and user-friendly. So something that takes the health into consideration, the health of the user, as well as the use of the user. So something that is easy to use, not something very heavy, something that is easy to grasp and easy to drink too. And of course, it's a project that is that has a high appeal internationally, and of course even within universities. Now for the weaknesses, we have problems like initial investments that is required. They could not meet probably our expectations. The production complexity, especially with manufacturing costs, and the precision into making the design, so the design complexity. For the opportunities, of course, it's a big market, Hydro Flask or mugs in general. There are a lot of brands that are known these days regarding this, of course. So our opportunities here involve features like thermal sensors and customization options. The user can customize the product as he wishes, and of course regular improvements of our product. For the threats, there are a lot of competitions, that's for sure, but we'll try to make sure that the competition is reduced by the price and the design as well. There are also economical factors, inflation, and the updates. It's hard to keep up with the market's demand. Now, for the project's needs analysis, of course, potential market, health-conscious individuals seeking better hydration solutions, environmentally conscious consumers, and so on. Of course, the design objective. As we said in the introduction, the design has to be agronomical and doesn't burn or put the consumer or the user into bad situations. The design also must cater the outdoor enthusiast, office worker, and the users in general. Now the constraint, we talked about them. Customer needs, we also talked about them. So they want at least, our objective is basically at least 7 hours of the thermal retention. Of course, easy to handle, easy to port, and most importantly, easy to clean. And this is what we gathered from the questions we asked some people, and these are the top 3. So last, the long thermal retention, easy portability, and easy cleaning. This is very important, and of course, sustainable for some. Now, for the black box function, of course, it is in the report, so I won't go through it much. We basically, in our report, we have everything is very well described. But if I were to describe it, I would say, it takes hot or cold beverages, temperature and time, and give us same beverages taste, same temperature, or at least a minor change in temperature. Of course, satisfied user. Now for the white box, here inside the white box we include insulation layers, good lead sealing, heat reflection, and vacuum or foam insulation, some kind of insulation that would keep the change in temperature very minor. Now the steeple analysis, of course, it is also described in the report, so I will go through it very fast. So for the social aspects, we want to address the growing demand for convenience in maintaining our beverage on the go. Of course, enhance the user's experience with a focus on usability, portability, and durability, and supports health-conscious consumers who need reliable hydration solution. Now, for the technological aspects, we want to utilize advanced 3D modeling, SolidWorks, to optimize our design and performance, and something that is very precise in terms of manufacturing. Now, for the economical factors, we believe that our product has potential for high manufacturing costs due to the quality of material and complex design. We try to target at least premium market. There's willing to pay for quality, durability as well, and opportunity to fulfill into the growing market of this product. Environmental, we of course talked about it many times, but here for our product we decided to use the inox 1.4301. It basically has 18% chromium and 10% nickel, and ensures longevity, recyclability of the flask. Now for the political and legal and ethical aspects, of course everything should be taken into consideration. It has to be our property first. It has to meet health and safety standards and ensures the product certifications and approvals of the market. Now here's a global market analysis of our thermal bottle. So, as you see, it's very commercial. This is by region, as you can see, and in North America, they're most used. They're also most used in households. But yeah, this is basically self-explanatory, so I'll just go through over it. Market trends as well. So I already mentioned these, the opportunities and the challenges of our product. So now, let's delve into the break-even chart analysis of the project. So here you can see a table of our materials and the price, so the total cost of our bottle. Okay, so these are the materials that are used and manufacturing as well, the design and so on. We get this break-even point. Now, going to the 3D model of our thermal flask. The 3D model of the isothermal mug was developed using SolidWorks. The tasks were divided, and so each one had a part to make. We also include each component alone, like straw holder. We include the straw in our flask, a cover as well that is well insulated, a mug, and to ensure functionality and also aesthetics. So the design process included a very detailed SolidWorks that we will go through later. Also a MATLAB simulation that helped us doing the mug, and helped us also analyze and simulate temperature drops, allowing for the evaluation of various insulation materials under different conditions. Finally, the results from simulations, they indicated that the chosen material is inox 1.4301 that we discussed earlier. So for the bill of material, as we see here, the one that suits best our expectations are, so we did this through MATLAB, is the inox. In terms of temperature drop as well, so metals are the most optimal. They're the most expensive though, but again, we're targeting users that are really concerned with that aspect. Okay, so the durability aspects, of course. Now, let's go to the dimensions. So based on many scratches actually, we developed SolidWorks drawing for each part. So for the first part here, we can see to the left the straw holder, which is an important supplementary part of the design, and it basically provides stability for the straw. It keeps it insulated from the mug, and it's usually made of a tight fit within the cover or within the mug itself. And of course, it forms a seal that minimizes heat conductance or leakage. Of course, a good straw holder should be made from material that does not burn or does not shrink, does not deform, and be able to accommodate all straw sizes, but at least ours for this case. But maybe we're looking for a design that fairly adapts with the straw size. But here it comes with our straw, which we designed. Okay, and it's probably it's actually glued to it, so it looks something like that. Okay, now to the right we have the cover, and it works as a core layer of insulation and ensures that heat does not transfer from the mug or from the outside into the mug. So either ways. Okay, so he keeps everything maintained. So this is typically built using a double skin or vacuum to increase thermal efficiency and hold in optimized temperatures. The cover should also slide tight over the mug. So basically one can screw, snap, or engage a gasket seal onto the mug to avoid spillage. Of course, the cover employs a slot or a place for the straw holder, as you can see here. It's basically the opening there, and can have a flap enclosure, which is basically the straw holder. Now, let's go first talk about the straw, because as we mentioned, our straw goes with the cover. So it's an important part here, and it's what makes people want to buy these kind of mugs. So several ergonomic studies have shown that the use of straw is preferred since it reduces the motion of lifting and tilting the flask to the drink, especially if the material is heavy, the mug itself is heavy. And hence the following picture shows the design of the straw. It's of course made of transparent plastic following the international standards for material selections as shown. Now finally the mug, our final design, and it has a handle as you can see, so that it's easy to pick up, and with the logo of our university, which shows green because our university is green. And yeah, so we'll talk about the handle in a minute, because you know our thermal flask should not be able to conduct heat into the hand of the user, so we'll talk about that after. Now this is the assembled view of our thermal flask basically. So once we take everything, this is what we get. And so several steps are followed when assembling the isothermal flask, in a bid to guarantee at least that it performs optimally and also is long lasting. So first of all, the inner and outer shell made of stainless steel are accurately bent, and were welded to produce vacuum chambers. Of course, there are also blankets of polyurethane foam. We can also use reflective coatings. They're basically added within these layers in order to improve the heat conductivity. Okay, so basically the bottle-to-bottle process of assembly ensures that flasks provide maximum performance and reliability. Now, let's pass to the FEM analysis and failure theory. So, failure theory, also referred commonly as the failure theory of failure criteria, is a core area of material science, a class that we're taking here at AUI engineering, that aims at identifying circumstances under which the constituent materials may fail under different loads. So this theory assists engineers in defining the limit at which a material can undergo stress, strain, or here in this case thermal deficiency or thermal expansion. So simple failure theory include maximum thermal expansion in this case. Now, the thermal analysis is what interests us more, and in the next section we'll analyze our isothermal flask, and we'll get emphasis into the design of the handle, which is, again, as I said previously, the most important, of course, part of our project. So as you see here, you can click on the link. So if you want to see the video of the FEM analysis, but it's basically described here. So as you see, of course, everything is self-descriptive. So the analyze was 2D simplified. Of course, you can do it in 3D. The video is actually in 3D. In fact, the SolidWorks simulation was in 3D. So of course, we considered our inox into our SolidWorks performance. We also considered that it's a linear elastic isotropic. And we also included some von Mises stress. So thermal conductivity here was 14 watt per meter Kelvin, and specific heat of our handle is 440 joule per kilogram Kelvin. The mass density is 7,900 kilogram per meter cube. And we also, of course, all the units are international units. So for the thermal loads, here the temperatures, as you see in this section, 70 Celsius, and initial temperature here is at 22. So what happens is, well, I cannot go back. Okay, well, it's fine. But basically, I cannot go back to the slides, but what happens here is that these materials also make it possible to isolate the heat from the flask body from the handle, and it allows basically the user to comfortably hold the flask without burning his or her hands dependent on the content. Using modern tools such as Simulink, that we'll talk about in a sec, but we didn't include it in our presentation due to time constraints, but also can do that. So the focus here was on the handle, okay? And yeah, so the MATLAB presentation is Yunsi's part.
So hello everyone. My name is Mohammed Younsi, and in this video, I will be explaining two charts that explore heat transfer and temperature drop under different conditions. So let's dive in. Um, so as we can see here, this chart shows how quickly hot liquid cools in mugs made of different materials. Um, the x-axis here shows time in seconds and the y-axis shows the temperature in degrees Celsius. We have three materials, as you can see: ceramic, metal, and glass. So here we observe that ceramic, represented by a blue line, cools the slowest because it has the lowest heat transfer coefficient, H equal 10, and a high specific heat capacity, C equal 900. On the other hand, we have metal represented by a red line which cools the fastest due to its high heat transfer coefficients, H equal 20, and a lower heat capacity, C equal 500. And last, we have glass represented by a yellow line which falls in between, with moderate thermal properties, H equal 15 and C equal 840. So, having said that, you might wonder why do we will use metal mugs even though they cool the fastest? Well, metal mugs have other advantages that outweigh their faster cooling rate. First of all, durability. Metal mugs are sturdy and don't break easily, unlike ceramic and glass. Secondly, we have portability. They are lightweight, making them perfect for outdoor activities like camping. And thirdly, there is the fast heating property. Although metal cools quickly, it also heats quickly, which is convenient for reheating beverages. And last but not least, the manufacturing and cost. Metal is easier and cheaper to mass produce, as demonstrated in the table on the right. So, so why ceramic is better for keeping drinks warm and longer? Metal mugs are chosen for their practicality and robustness in real life situations. Now let's move to the other charts. So this chart examines how the presence of flow impacts the cooling process over time. In here, the x-axis represents time in hours, and the y-axis represents the temperature in degrees Celsius. We have two different scenarios, which are plotted in here. The first scenario is that flow not computed, blue line with crosses, as you can see. And the second is with flow computed, the green line with circles. The results are interesting. In both cases show a gradual cooling trend, but the flow computer scenario shows a slightly faster cooling rate. This happens because the presence of flow enhances the convective heat transfer, which accelerates heat dissipation, and this concept is widely applied in engineering, especially in systems like heat exchangers and thermal management solutions. So that was pretty much it. Thank you for watching this explanation, and I hope you found it insightful.
Now, to conclude, the project on designing and developing an advanced isothermal flask, or isothermal mug, whatever you want to call it, has been a comprehensive and insightful journey for all of us. Utilizing powerful tools such as SolidWorks and MATLAB allowed us to craft a flask that excels in thermal retention, durability, and user convenience. So our material selection process and thermal analysis, particularly on focusing on the handle's non-conductive properties, ensured both safety and performance. And of course, the project demonstrated an effectiveness of eco-friendly throughout. It's also innovative. There's a design that is unique. And from the market analysis to cost evaluation, every aspect has been thoroughly examined to bring forth a product that not only meets but exceeds industry standards. So the successful development material wouldn't be a thing without a supervision. And this supervision goes to Professor Rashid Lahoud, who has followed or helped us with the project through the classes, the computer engineering classes. So thank you everyone, and thank you, Professor.